So of course we have to do some calculations with this. So here's the equation. The heat required to change the temperature is going to be equal to the mass of the object times the specific heat capacity times the change in temperature. The more substance there is, the more heat it's going to take, right? And the bigger the temperature change, the more heat. So if you think about boiling some water, say you're going to make a pot of spaghetti just for yourself. So you maybe just need like 1 or 2 cups of water, and it's not going to take long to boil. If you're making spaghetti for the varsity football team and you've got this ginormous pot of water, it's going to take a long time, 45 minutes. Had to do that. 45 minutes for the water to boil. Good grief. Because there was so much of it. The temperature difference affects the amount of heat also. If you start with hot water, it doesn't take as much heat, as much energy to get it to boil because it's already close to the boiling point. If you start with ice water, it's going to take a lot more energy, right? So the amount of heat depends on the mass and on the change in the temperature. So it's a little hard to see because it's all spread out there. But the equation here is Q equals M capital C delta T. So students sometimes refer to that as MCAT because the delta kind of looks like an A. That delta, the triangle, is the Greek letter delta, and that means change in. That's what scientists use it for. So the change in, it's always the final minus the initial. So delta T would be the final temperature minus the initial temperature. Okay, so you find a copper penny in the snow and you pick it up. How much heat is absorbed by the penny as it warms to from the temperature of the snow, minus 5 degrees Celsius, to the temperature of your body, 37 degrees Celsius. Assume the penny is pure copper and has a mass of 3.10 grams. You can find the heat capacity of copper in table 3.4 on page 71. That would be of the 5th edition of the book. Let's just go back here and find copper. We're going to need that, 0.385. So I'm going to write that down. 0.385 joules per gram degrees Celsius. Now, this word problem is like a big step up from the other ones we've been doing, right? There's a heck of a lot of words in there, and there's a whole bunch of numbers. Same approach. Read the question, go through, pull out the numbers, and sort them. Okay, this pre-1982 business, that's not going to come into our calculation. In 1982, they changed the composition of pennies. They used to be solid copper, and now they are not. So we've got minus 5 degrees. So we'll write that down. And we've got 37 degrees. And we've got 3.10 grams. And what's it asking? What is it asking? Here's the question. How much heat? So this is a temperature, right? And this is a temperature. The equation we're going to need here is Q equals MC delta T. Delta T is the final temperature minus the initial temperature. Delta T can be positive or negative. If something's getting colder, it's a negative change. If it's getting warmer, it's a positive change. So we have two temperatures here. Which one is the initial temperature? The minus 5, right? The penny warms from minus 5 to the temperature of your body. So this is the initial temperature, and this is the final temperature. So we can put those numbers in here and find out what the change in temperature is. Be 37 minus negative 5. And so that's going to be 42.0 degrees Celsius. 3.10 grams. What's that? That's the mass. And so when we're looking at this equation, we're trying to find Q, how much heat. We need the mass. Got that. We need the specific heat capacity, which we looked up. That's this guy right up here. And we need the change in temperature. So we've identified MC and delta T. We just need to put them into the equation. Q equals the mass, 3.10 grams, times the specific heat capacity, 0.385 joules divided by grams degrees Celsius, times 42 degrees Celsius. .1 times 0.385 times 42. So 50.127. All of the numbers in there had 3 sig figs, and so this is going to have 3 sig figs, and it's going to take 50.1 joules. It absorbed 50.1 joules of energy from your hand. Any questions? You have to read the question and be willing to go in there and pull it apart, sort of like untangling some string. You kind of have to pull it bits until you see, oh, here's an end, I can follow this, right? These questions are not going to be obvious. Oh, this is what I need to do. Occasionally they will, and then you can just be real happy.
So is that TF minus the TI?
Yes. Yeah. Final minus initial. My F didn't come out very well. Any questions?
And in case we ever have something like a conversion
Mhm.
where you have Fahrenheit, we would have to first convert the Fahrenheit to...
Right. You definitely want to write your units in here, and I should have pointed this out. Look how the units cancel. The grams cancel, and the degrees Celsius cancel, and what I'm left with is joules. If you have this temperature in Fahrenheit, it's not going to cancel the degrees Celsius. And so you need to make sure that your units are going to work out. Any other questions? The temperature of a lead fishing weight rises from 26 degrees to 38 degrees as it absorbs 11.3 joules of heat. What is the mass of the fishing weight in grams? Because it seems like it would be easier to just weigh this stupid thing, but we can't do that because it's the problem. So pull the numbers out. We got 26 degrees Celsius. We have 38 degrees Celsius. We have 11.3 joules. And it's asking, what's the mass? So that's the M. We've got heat, we've got temperature changing. We're going to use Q equals MC delta T. But this time we're not solving for Q. We're solving for M. We need to rearrange the equation. So we want to get M by itself. M has a C and a delta T with it. We want those to go away from that side of the equation. If I divide by C, the C's will cancel out. And if I divide by delta T, the delta T's will cancel out. But now my equation isn't true anymore. I have to do the same thing to both sides. So whatever I did to that side, I need to do to this side. And then that's a mess, and it's kind of hard to look at. So rewrite it. The mass is going to equal Q divided by the specific heat capacity and the change in temperature. So I've got two temperatures here. Which one is the initial temperature and which one is the final temperature?
The initial is 26.
Yep, the 26 is the initial and the 38 is the final. And it's the words that tell us from 26 to 38. So then we can calculate delta T. Delta T is the final temperature minus the initial temperature. So it's going to be 38 degrees Celsius minus 26 degrees Celsius. And I'm pretty sure that's 12, right? That's our delta T. This 11.3 joules of heat, what's that? That's Q. Q stands for heat. Don't ask me why. What are we missing? So we've got the Q, we've got the delta T. We're missing the specific heat capacity. So it says it's a lead fishing weight. It's made out of lead. So we have to go look this up. So the specific heat capacity of lead is 0.128 joules per gram degree Celsius. C equals 0.128 joules per gram degree Celsius. So now we can plug these in. Q is 11.3 joules, and we're dividing by specific heat capacity, 0.128 joules per gram degree Celsius, and the change in temperature, 12 degrees Celsius. Degrees Celsius will cancel, the joules will cancel. What we end up with here for the unit is 1 over gram. So it's flipped over twice, so that's just grams. When you do this on your calculator, you need to be careful because it's 11.3 divided by 0.128, and it's also divided by 12. Students tend to do 11.3 divided by 0.128 times 12. If you're going to do that, you have to put parentheses around the denominator. You have to put parentheses here if you're going to use the multiplication sign. So 11.3 divided by parentheses 0.128 times 12, close parentheses, equals. This is going to have two sig figs, 7.356, 7.4 grams. Any questions?